Contortions. Katrina, Ben, Shay, and Drew.
Woo! A contortion is a twisted position, like pasta. Some examples of contortions include twisted DNA, knotted rope, links and chains, and pasta.
Whoa. Knots plus links equals math. When we try to disentangle a loop of knotted string, we sometimes wonder whether we are making matters better or worse. This question leads us to the important idea of measuring the complexity of a position of the string. By deciding on some way to gauge the complexity of a knot, we can see if we are making progress towards disentangling it. This strategy of measuring complexity is highly applicable to mathematics and life as well. It allows us to tackle complicated issues a step at a time.
DNA itself is a contortion. Think about it. So there's about 6 feet of DNA within every cell, which is the smallest unit of life, and 6 feet is about as tall as my boyfriend, so that's pretty huge. That condenses all into the smallest unit of life. And with a quick Google search, I found that so there's about 6 feet within every cell, and if we're going to just lowball estimate, say that we have about 10 trillion cells in the human body, that means you have 60 trillion feet of DNA, or about 10 billion miles. So that within itself is contortion because it can fit into a cell that you can't even see. But the book gives an example on the DNA and saying that it's about its replication. And we all know that DNA is in a double helix structure, and when it replicates, it needs to split down the middle, and so you can get new strands. But mathematically, it's impossible take, for an example, if you take 2 pieces of string and twist it around each other thousands of times and then try to pull it apart, it will wind up and knot and, just generally be messed up. So because it's mathematically impossible, mathematicians pretty much told the scientists, like, hey, go look at it again. And that's when they found enzymes to help relax the DNA so that it doesn't get wound up, enzymes that hold the DNA strands on either end so they can't intertwine or mingle. And I want to say it's a slow process, but it can't be terribly fast.
Reduce the complexity of a problem. Take untangling a knotted rope hanging from the ceiling, for example. At first it may appear that one could unknot and unlink the tangled and knotted rope without removing it from the ceiling. Measure the complexity of a situation and work to reduce it. Suppose that a way exists to remove one of the crossings of the tangle, and that this method does depend on the idiosyncrasies of the tangle itself. By removing this crossing, we would have another tangle, but the tangle won't be quite as complicated. If we repeat this procedure, then we reduce the number of crossings again by 1. Doing this process over and over, you will eventually untangle the rope, and you will end up with a rope with a loop.
Is it possible to link 3 rings together that they are indeed linked, but if one is unlinked, the other 2 also become unlinked? Yes or no? It is possible. In the borromine rings, no 2 rings are linked, so if any of the rings are cut, all 3 rings fall apart.
The Olympic rings. It's generally known that the 5 interlocking rings represents the 5 continents of the world: the Americas, Europe, Asia, Africa, and Australia. The reason why the 5 rings are interlocking is because it represents a continuous, ongoing loop. The rings can't support each other without one another. The blue ring is connected to the yellow ring is connected to the black ring is connected to the green ring, and the green ring is connected to the red ring.
The Gordian knot is one of the most famous knots in history. The Gordian knot held a mythical sway over the people in the 4th century. The one who can untie the Gordian knot will be the Lord of all Asia, is what the legend of the Gordian knot used to be. Then Alexander the Great arrived, and he was confronted with the Gordian knot. So he just cut it in two. I mean, it fulfilled it, but that's cheating. He's a cheater.
Okay. The Brouwer fixed point theorem. Suppose 2 discs of the same size, one red and one blue, are initially placed so that the red disc is exactly on top of the blue disc. If the red disc is stretched, shrunken, rotated, folded, or distorted in any way without cutting, and then placed back on top of the blue disc in such a manner that it is not hanging off the blue disc, then there must be at least one point on the red disc that is fixed. This is, there must be at least one point on the red disc that is in the exact same position as it was when the red disc was originally on top of the blue disc.
Two discs, identical in size, red disc is malleable, blue disc cannot be changed. Each point of the 2 discs match only one point. Can you find a distortion of the red disc so that once it is placed on top of the blue disc, no red point is paired with its original blue partner? Twist it like a record player, folding it in half, then half again, crumbling it up into a random shape.
The meteorology theorem. At every instant, there are 2 diametrically opposite places on Earth with identical temperatures and identical barometric pressures.
Every location on Earth has exactly one point that is diametrically opposite. Take a globe. Only pressures and temperatures marked. There will always be 2 points that are the same. Taking the Brouwer fixed point theorem, there are only 2 points on Earth at a time that will have the same temperature. These points are generally on the opposite sides of the Earth.
The hot loop theorem. If we have a circle of variably heated wire, then there is a pair of opposite points at which the temperatures are exactly the same.
Label a circle like a clock. This will help us with temperatures. Point 12 equals 78 degrees. X equals temperature X. Consider the difference between opposite temperatures. Temp 12 minus temp 6. Temp 12 is hotter than temp 6, keeping the temperature positive. Temp 2 minus temp 8 is still a positive number, meaning that temp 2 is hotter than temp 8.